Okay, so there's a population with 426 people, and the genotype frequencies in the population are homozygous dominant 121 people with this genotype, 211 people with the genotype of heterozygous big A small a, and then 94 people with the homozygous recessive allele genotype. So for this locus, right, the dominant and recessive big A small a locus is this population in Hardy-Weinberg equilibrium. So the way to solve this problem is just to write out what you know, right? And then the next thing is to find the frequency of one of these, right? To find the frequency of either P or Q, because that would allow us to reverse engineer the problem and then see if the theoretical would match what we're given right here. So to find the frequency, we have P is equal to, so we just chose this arbitrarily, right? You can also choose Q, but we just chose P, right? And now we just want to find the raw amount of alleles, right? So the total number of alleles, because what is P, right? P is just the frequency of this allele in this population. So then first we'd have to find on the numerator the total number of P alleles, which would be the big A alleles in this population over the total amount of alleles, right? A proportion, just like in like any other example in life. And so we'd have the total frequency of A, right? Which would just be 2 times the homozygous dominant frequency plus the heterozygous frequency over, and so notice how we have to multiply the entire population, which is 426, by 2, right? Because there's 2 alleles per person, and we're trying to find the frequency, so that require of the alleles, right, not the genotype. So we'd have to find the raw amount. So we'd have to multiply 426 by 2. And so then we'd also have the frequencies on top. And so moving forward, we would just plug that in. So we'd have 2 times 121, because that's the frequency of the homozygous dominant, and then the 211, which is the frequency of the heterozygous, over 426 times 2, because that's the raw amount of alleles. And so that would equal 453 over 852 is equal to 0.532, right? So this is our P, right? This is our P frequency, the frequency of which the P allele occurs, because P squared is the genotype, right? The frequency of which the genotype occurs. So this is 0.532. Now we can solve for Q. Q is equal to 0.468 after you do this, right? This is the other equation for Hardy-Weinberg. And so this just 0.468 tells you the frequency of which the Q allele occurs, right? Make sure you notice the distinction between the allele and the genotype frequency. So for the theoretical, right, to answer the question, since we now know the frequencies, we need to find out P squared for the theoretical Hardy-Weinberg population. So P squared, remember that this, right, 0.532 is P, not P squared. So it'd actually be 0.532 squared, which would be 0.283 times 426, right? We can't stop right here because even though this is P squared, we're trying to find it for our population, which is 426. So that'd be 120.6 people, and then 2 times PQ, right? And then once again, it would be 2 times P, right? P and times Q. So it'd be, in this case, we would be using these numbers. We would be using 0.532 times Q, which is 0.468, which would give us 0.498, right? And so then it would be multiplied by our population to get the actual number of people, which would be 212. And then finally, Q squared, once again, this is just Q, which is the allele frequency, and we're trying to find the genotype frequency. So it would be 0.468 squared, which would be 0.219, times our population, which would be 93.3. Now what we have to do is compare it to the numbers we were given. So the numbers we were given are 121, 211, and then 94. So we just compare it, and they're pretty close, right? Because we have 121, which is what we were given, 211, and then 94, right? So they're all really close. So we can say that this population is in Hardy-Weinberg equilibrium. And so I just want to show you a faster way of solving this problem. So you can have your homozygous dominant, right? And this is the genotype frequency, p squared. So we were given that there's 121 people with this frequency, right? So it's 121 people over 426. So that would give us p squared is equal to 0.284. So then if we find the allele frequency, it'd be 0.533. And then for homozygous recessive, it'd be q squared is equal to 94. We were given that 94 people have this genotype frequency. And so it'd be over the total number of people, which would equal 0.220 for the q squared. And then square rooting that, you get 0.469. Now if you just add these two together, you get 1. And so that also shows you that you're in Hardy-Weinberg equilibrium. Now, one last thing I just want to go over to make sure you understand. Notice how over here we had to multiply by 2, right, for the heterozygous frequency, or I'm sorry, homozygous dominant frequency. But here we didn't do anything to the heterozygous frequency. We didn't multiply by 2 or divide by 2, right? Because the reason is, if you think about it, you have a 50-50 split between the alleles, right? So if you have 8 people with the heterozygous allele, you would have 8 individual big A's, right? And then 8 little a's. And to illustrate that, over here, right, the reason why we don't have to multiply by 2 or divide by 2 for the heterozygous is just the fact that since we have a 50-50 split, right, so we have 8 people with a big A, little a, well, if I asked you how many, for the heterozygous population, how many big A's are there? Well, there's 8, right? There's 8 big A's. And then for this population, how many small a's are there? Well, once again, there's 8. So that's why we don't have to change it. We don't have to multiply by 2, because if they're telling you that there's 211 people, well, that means there's going to be 211 big A's or small a's. So in this case, since we were calculating the big A frequency, we know that there's 211 big A's. So I hope that helped, and thanks for watching.